Welcome back, and thank you for continuing the training school. So in the last hour, we heard, after a few administrative updates, a bit of motivation for why we are interested to calculate charge transport, and we saw one specific application of the electric materials. So we'll continue a bit with examples of case studies. And this example is about the semiconductor. If before we talked about the electric material side, now the major transistor component is the semiconductor, molybdenum disulfide. You can see here on the right the unit cell. From the side view, I'm on a layer of molybdenum disulfide, and on your left side and on the right is a top view. The big yellow bulb is again a charge density difference that we do in DFT calculations to see how a vacancy changes the charge distribution as a result of its absence. So we can see a large deficiency of charge where the vacancy is at. And here we can see on your left, on the left panel, the density of states. This is something whoever is doing DFT calculation is normal to looking at the number of states in the y-axis as a function of the energy for different concentrations of vacancies. We have the 11% and the 4% amount of vacancies. V2S just means that the vacancies are also clustered. It's effectively a larger concentration of vacancies. And so what we can see in the density of states is that the material has a band gap of above 1 electron volt. And then when we add more and more vacancies, you can see in the arrow a trap state is formed. And also the edge of the conduction band moves to lower energies on the scale. These are defect states that arise from the vacancy. And on the right, you can see some analysis of the atoms close to the vacancy. So we have the nearest neighbor molybdenum atoms close to the sulfur vacancies, and they are the ones that are actually having a surface, another surface trap state. So as a result of sulfur vacancy, there is excess charge located on its vicinity, atoms on the molybdenum atoms, and energy on the energy scale, it's on these trap states and at the edge of the conduction band. These states will contribute to the current, the electronic transport through the material. So the idea in this work was to check on how the most abundant type of vacancies, sulfur vacancies, in what is considered the most abundant semiconductor in two-dimensional transistors, which is molybdenum disulfide, how they affect electronic conductivity. And these are the results that we can get from the code. What is called the probability for charge transport across or through the material as a function of time for different amounts of concentrations of vacancies. Of course, if there is no vacancy at all, we can see in the black, the transmission is the highest. The electronic conductivity in the material is highest. And it's lowest in the gray, which is clustered sulfur vacancies at 11% concentration, huge amount of vacancy. By the way, in monolayered materials, the probability of a large amount of vacancies is higher than a bulk material. So it's expected that there will be a large amount of vacancies, but for the sake of checking the trend, we just increased more and more. There's also a a distinction between solid lines and dashed lines. So solid line is where the electron average and initial energy, the incoming electron that starts to transport, has an energy located at the mid-gap states, at the trap states, just to see the contribution of those trap states to the overall current. Whereas the dashed lines are a transition at the conduction band. We give the electron an initial energy of the conduction band. As we will see later in the exercise, we can control and decide what the initial energy of the electron is when it starts to enter and transport through the material. So we can give it at the edge of the conduction band, we can give it a mid-gap state. So you can see the mid-gap state is not so trapping at all. It actually is a large contribution. The dashed line is quite high. And we did different analysis techniques using what we will not discuss today, non-transmission quantum mechanics, to see that that state is not really bound. It's part of a continuum and it contributes to current. So I think the main conclusion here is that vacancies, of course, intuitively lower the current, but it's more than that. It demonstrates how controllability the code, controllable the code is. You can decide on the initial energy of the transferring electron. You can change the amount, the system as you wish, the number of vacancies. A different system that was studied is an interface between two disulfide materials. So you can see here two different colors for two different transition metal disulfides. And the list of materials is here. So the blue would be either chromium, molybdenum, or tungsten. And a longer side, the gold colors are either iron or vanadium. So the long side is the metal side, and the short side is in this unit cell is the semiconductor. In the simulation of charge transport, the thickness of the distance has some role, and the metals usually need, because of the delocalization, usually need larger sizes. But as we will see in the exercise, it doesn't really require a large DFT calculation in a large unit cell. You can simply elongate the potential of the material as much as you want, and with our code, you don't really need to do this additional large DFT calculation. You can circumvent this with our code. And here are the results, the transmission probability as a function of time for the different interfaces. So on the left, it's with a metal vanadium disulfide, and on the right, it's a metal that is iron disulfide. And the reason for selecting these is that they will have the same structure as the semiconductor, molybdenum disulfide, for example. If the metals are similar to the semiconductor in structure, then the adhesion will likely be large, then the connection will be large, the transmission coefficient will be large. And the best functional material seems to be vanadium disulfide and chromium disulfide interface with the highest transmission probability of them all. So the code also gives us the ability to compare between materials and find trends. Another application highly relevant for this cost action is catalysis or electrocatalysis. And this is a schematic of an electrochemical device. So we have here an electrode and a cathode and anode, and on the surface, a water oxidation in this case is happening. So modeling the interface of iron oxide with a back metallic contact is relevant for best performance. In DFT, we usually model heterogeneous catalysis, but the solid-solid interface on the back is also important. And here you can see a selection of interfaces. The lower part is iron oxide, and the upper part is different metals, silver, aluminum, gold, iridium, palladium, and platinum. And so this method is computationally so fast that you can use it for a large amount of materials and compare between them. And out of all of the metals, the one with the highest transmission probability is iridium, actually. And as we will see later, the methodology circumvents the need to do large unit cells in DFT because you can take the potential energy of the materials and average them. For example, if you want to treat an alloy. So in this unit cell, your left side includes an oxide, and the right, you can see two colors here. The one in yellow represents a gold atom, and the one in gray represents a silver atom. So it's an alloy of silver and gold. And you would think that for an alloy, you need a very large unit cell to do the DFT calculation over again, because our code uses the output of DFT. But we don't really need to do it. It's enough to average results of the two parent materials from DFT, the mass calculations from the two parent materials. And that's sufficient information that we demonstrate that it gives the same transmission probability as if you would do a large DFT calculation for an alloy. And we'll see how to do this averaging of potential energies to extend the potential energy to mimic a large unit cell in the tutorial. And this is demonstrating again that you can really look at the electron as it transfers through the material. The blue is the position of the electron at the beginning, the wave function. The red is the potential energy of a material that you get from Concham, the one that you take if you do work function calculation. So it's the potential energy of the material, and we'll discuss this more later in this hour, what this red area means. But the position of the wave function is such that it starts from the left side, from the oxide side at the beginning. This is the initial position, and the code is very, very flexible. You can use any initial position you want. You can start it on the right, or you can start it away from the surface interface. After some time, as any wave function or dynamical calculation, the wave function expands. Some scatters, some is able to transfer to the right, some reflects back. And at very large simulation times, it gets to the edge of the box and reaches equilibrium. When modeling iron oxide contacted with a metal, there's different considerations to take into account. Here you can see a unit cell in the center of iron oxide. The reds are the oxygens again, and the browns are the irons, and the grays are the platinum. And when you model a material, its crystal structure orientation is very important. So what we get in VASP is a three-dimensional potential energy, and what you get when you do work function calculation is usually average over some surface plane and get a one-dimensional potential. And with that, you can continue with our code and do dynamical calculations. But the structure of the material and the bonding and the octahedra connection and the coordination of each atom could affect charge transport probability. And as a result, we did some generalization to the code and didn't use a one-dimensional potential energy, but a two-dimensional potential energy. The most important axis here is the direction normal to the interface. An electron that starts on the left and needs to pass through the two materials. The important direction is this z-axis, the normal to the interface, where it needs to pass. But the dimensionality of the material itself is also important because there could be additional scattering in low energy directions for charge transport. So in this study, we actually propagated the charge in a two-dimensional contour to test how the one-dimensional approximation, how well it is. So this is how the wave function looks like when we look at it in two dimension. This is the z-axis. This is the x-axis. And you probably cannot see the wave function. It's a red dot here. Starts from the left, from the oxide side. So this is a T0. And after some time, you can see the wave function scatters in all kinds of directions. And these directions correlate with the electronic structure of the material. It goes through bonds that have low energy and can pass through them. Then after more time, the wave function scatters to larger distances. Whatever can pass to the metal side passes, and whatever is not, it stays at the oxide side. The nice thing about this research in this case is that two materials were compared, platinum and silver with iron oxide. And here platinum showed larger transmission probability than silver. But the point is that this trend was consistent both in the one-dimensional model and in the two-dimensional model. So it's not really necessary to do a heavy simulation with two dimensions because the bonds of the material, the chemical bonds of the material are what they are in either one dimension or two dimension. So their distance, their electrostatics, their geometry, you see all of their properties also in the one-dimensional model. So at least qualitatively, comparing between materials is possible on the simple one-dimensional model, which makes the code really fast. You do the simulation in only one dimension. I think this is the last application, the alumina interface. So you can see this model, the silver atoms are aluminum atoms, the red atoms are the oxygen atoms. So the left is the oxide, alumina, and the right is aluminum. So this is a top view of it, you can see on your right. And this material, this interface is used a lot in the industry for quantum computing. We decided to model a lot of types of defects at the interface. So this is an interface without any defect. This is when a hydrogen atom penetrates. This is with a vacancy. And there's much more. There's a hydroxyl group here, and then double O2 that might come in from the atmosphere, depending on the fabrication condition. And in this area, the intrinsic defects might affect a lot the electronic conductivity through the qubit. And if there's any interference at all, it will completely destroy the two-level system in a qubit. And it has been a debate where in the material intrinsic properties, the noise in the electronic conductivity comes from, well, the qubits fail in the fabrication process in the industry. So we modeled all possible defects that have been suggested in the literature and that we could think of, and calculated charge transport along the interface. What you can see in the top view is a wave function, the initial location of the electron. And in the black is the potential energy of the material that you would take from DFT when you do work function calculations again. And so it starts from the aluminum metal, scatters, and the final state is that some is able to transport to the oxide and some reflects back, stays at the metal side. So this is how the simulation looks. And we check the simulation for each unit cell with each and every one of possible defects. And you could see that the defect that gave the best comparison to the experimental noise was when a hydroxyl group was attached, an OH group was attached at the interface. And this is something that could result from the atmospheric conditions of fabrication, maybe humidity, at the fabrication conditions at this interface. So we could do a transform Fourier of the charge transport probability as a function of time to the frequency domain and receive what is measured experimentally, which is the power spectral density. And we found that the one that shows the best fit to that spectral signature was the hydroxyl group. So this gives us a prediction of first where the noise comes from, and second how to avoid it during fabrication. So to summarize this introduction, we've seen that the algorithm was tested in a variety of systems and applications. You can really use it for whatever system you are currently working on in your PhD degree or research. I know some of you are researchers. The approach enables to really look at the electron as it transports through. This gives us a lot of insight. And the method is useful for designing new materials because the calculations are quite fast. You can use them on a lot of materials. And the second part of the talk, I'm not sure how much I'll manage to get into the rest of the time we have. If not, we'll continue in the computer room before the exercise. But I'd like to go more deep into what the code actually does. And so we will talk about what is the potential energy of the material. This is what you get from your DFT calculations. How to set the initial condition of the location of the electron, how to solve the time-dependent Schrödinger equation, get the time-dependent wave function, the solution of the Schrödinger equation. And finally, we'll talk more about what is the flux as an observable and how we can calculate from it the electronic current. Okay. So if we want to see anything that is dynamic, we must solve the time-dependent Schrödinger equation if we want to consider quantum effects at least. And so you have here H bar, delta t, to dt, first derivative of the time, the wave function, and it equals the Hamiltonian. The only input you need to know to solve this is the Hamiltonian and to know how to implement it numerically and solve this equation. The Hamiltonian includes both the kinetic energy, which is in general, it doesn't depend on the material, and the potential energy. The potential energy, we know a potential energy definition is a potential that depends on distance. But in our case, it's not just any distance, it's distance in a material. So I call this potential energy of a material, what the electron sees, the hills and valleys, while it transports through the material. For a periodic system, we would expect the potential energy to be just periodic, like this, where the minima energies, the values would be, for example, electronegative groups that trap electrons, or the place where the core electrons lie. And the barriers are the kinetic barriers, barriers that the electron needs to pass or overcome. The height of these barriers should intuitively be high if we have an insulating material. And for a metallic material where the electrons are essentially free, it should be flat, ideally. But when we do a DFT calculation, then you will actually see that it's not completely flat, it has some curvature, resulting from the core electrons that gave trapped electrons that gave it a curvature. And for an interface, when you bring together two different materials, then on the left, you will see barriers for the metal side. On the right, you will see barriers for the insulating side. And between them, a new chemical bond is formed. And it's typically high if the materials are completely different. Then it's difficult to transfer. This is the dominating barrier that the charge needs to overcome to transfer from one material to the next. This barrier is actually something we can control for material design. We can mix and match two different materials and get the barrier to be as large as we want, depending on the material type, because it's a new chemical bond that is formed between the materials. So here you can see two atomic models with two different metals, gold and silver. And usually when we have an atomic model, the conventional method in our field is to use density functional theory and obtain all information you can about the stationary states. The approach we are saying is not to stop there, just in order to see dynamical information and not just stationary information, but to take the potential energy of the material, which you have because you use it already. You have it, it's in the log profile of VASP. It's the potential energy we usually use in our field to get the work function of materials. To use that potential energy, plug it into the time-dependent Schrödinger equation and solve for the wave function as a function of time. This is a differential equation whose solution is the wave function. So generally what you get from VASP or any DFT solver is this black line shown here schematically, the potential energy of a material. You can choose with our code where to place the initial condition, the initial location of the electron. You can put it on some atom or some side or a few atoms of the material. And then you'll find that the code is quite controllable. You don't have to have a big unit cell in DFT. In our code, you can simply continue and extend it manually, extrapolate the code more and more, and then you'll have a system of much more atoms than you could do in a DFT calculation. You can also mimic some defect if you manually increase one of the barriers. For example, if there's a dopant or a vacancy, you can put one of the barriers upper or higher. So it's so controllable. You can really tune each and every place in the potential, and you don't have to do a big DFT calculation with the defect if you can anticipate the size of these barriers. One more thing we played with is we could make this potential time dependent. We took one of the barriers and vibrated it because that defect in the alumina interface, the hydroxyl group has a vibration, which also affects the signature that is seen experimentally in the current. So here you can anticipate how the potential energy of a material looks like if you have a defect at the interface. You can see the blue is high in case of vacancy or a defect, and the red is without any defect at the interface is lower. And this is an example of how a real potential energy looks like. The left is a schematic, and the right is actually taken from DFT, as we've seen before for the silicon carbide electric material. This is for the alloy case of silver and gold with hematite. So you can also see at the interface a large barrier, and the potential is extended at the simulation level, not with DFT. We have a huge system at the simulation level. You can see a contour plot of the potential energy in 2 dimensions. We plot it in 2 dimensions, not only in 1 dimension, for the system of iron oxide and platinum. So just to look at how potential energy look like of materials. We also have an algorithm to do high throughput screening, but I'm not going to go into that. And there is an option to parameterize the model and find correlations to see if the height of the barrier is most affecting the transmission, or the width of the distances between the atoms in one material. There's a lot of potential for further analysis and understanding. And finally, I'd like to mention what the code is actually doing. So we have several codes in our group, as I said, that were used along the way. We have Mathematica by Ofer, and MATLAB was used by Liora. And the first thing the code does is to import the output that we got from DFT, the log pot potential, which is the file with the potential energy of the material. And when you look at the code, it's just to read it. Just to read the file. It's just reading the logpot file. See, it's logpot. You might be familiar with this output file from VASP. So it's just reading it. That's a single line about. I told you the codes are really short and you can write it on your own. Then there is an initial location of the charge. In dynamical calculation, this is just a Gaussian wave function. And you can see the exponents of z in the power of 2. Z0 is the initial location, P0 is the initial momentum, and sigma 0 is the width of the uncertainty in the initial position. So this is and again, one line of code that just defines the initial position where you want the electron to be and the energy of where you'd like it to be. The initial momentum can be evaluated based on the kinetic energy of the conduction band edge as calculated from VASP. It's actually analytical. If you know the wave function and you have the kinetic energy, which is a second derivative, then it's possible to get this equation analytically for the kinetic energy. And the potential energy is calculated numerically. Just checking my time. Yeah, so okay. So I would like to write some things on the board. I'm just thinking of how to do it. One. I'd like to summarize what we learned so far and then continue in the computer room. So we'd like to solve the Schrödinger equation. And so we have I h bar. First derivative of the time, the wave function, time dependent, and our Hamiltonian. And this needs to be solved. Notice it's called ordinary differential equation, depends on the relative time. In order to solve this, we need some information. We need the initial condition. And this is something the user can specify, as I said, size or the electron will be at the beginning, the initial energy, the initial location of the electron. It can start on the left side, and one material, the oxide, or the metal. And what you need from BFT is the potential energy of the material. This depends on the distance, and if you take it only in one dimension, then you can decide to look at charge transport along a given direction. So this is taken from BFT. So to summarize, we learned that all you need from BFT is the potential energy of the material. It has a given shape, which is generally periodic. We see more of its shape for very common semiconductors, such as gallium arsenide in the computer room later today. And the initial wave function, we take it to be about a simple Gaussian, which is located on a certain position in the material. There's a lot of information about what the code is doing, so we'll discuss it more deeply in the computer room, but we have the job of the hour, right? So I'll put the lights back. Why can you never trust atoms? They make up everything. So a lot of the applications we've seen today show the diversity of systems that we can use for our code. You can do high throughput screening with our code. You can mix different atoms to make up everything, to make up an interface, to make up the bulk. You can treat alloys with our code. So I hope you find this very useful. And now the next thing in the program, the hour is, I think, 11 and 13. So at about 11:15, a guide will come here to this area in front where we had the pastries before. And we'll take you to the visitor center. I'll guide you. I'll show you who's the guide. He will come in about 2 minutes. Someone is opening the door. Maybe that's him. So you can see behind you, I think, the guide from the visitor center. I think Are you from the visiting center?
Yes.
Can you say your name?
I'm
Abdallah. So this is your guide. You can follow him now, right? When you feel ready, take a few minutes to pick up your things. And when you'll be back here at the 1:15 for lunch, right? You'll take him back here at 1:15 because lunch will be served at the same place here in front of the auditorium, okay? Thank you very much. See you later. שנייה, אני רק מפסיקה את הרקורדינג.